When you start an engineering degree, you are faced with many challenges and questions, and today we are going to try and answer one of them. That is, what is engineering mechanics? You may have noticed this word mechanics seems to show up a lot in many of the courses you have to take, from early courses on statics and dynamics to later courses on fluid mechanics and fracture mechanics. What is meant by this term, mechanics? Let's start with what it is not. Don't confuse the word mechanics in engineering with the profession of a mechanic. Although in engineering you will learn the wonders of WD-40 and duct tape for fixing things, this is not the core of what mechanics means in an engineering sense. For engineers, mechanics describes the behavior of bodies in terms of a state of rest or motion when subjected to forces. There are three key words in this definition: bodies, motion, and forces. What do we mean by these terms? The term bodies refers to any physical object, such as an aircraft or a rocket, but could really be anything, even a potato. In lots of mechanics textbooks, you will see generalized bodies drawn as potato-shaped blobs like this. We will often use such a representation of a body when introducing new concepts in this course, and you will often hear me refer to it as an engineering potato. Motion is a more obvious term. It refers to how a body moves, including both translation and rotation, as well as speed and acceleration. This leaves us with forces. Forces can be defined as interactions that will change the motion of a body if they are unopposed. How can we think about that in practical terms? If we want to move an object, we can either push it or pull it. So we can think of forces as a necessary push or pull to cause motion. Lucky for us, a really smart physicist by the name of Isaac Newton came up with some handy laws to describe the interrelationship between forces, bodies, and their motion. As smart people tend to get their name attached to smart things they do, these laws are aptly referred to as Newton's three laws of motion. So let's briefly review these laws. Newton's first law states that every object persists in a state of rest or uniform motion in a straight line unless it is compelled to change that state by forces impressed upon it. In other words, bodies are inherently lazy and do not want to change their state of motion. You require a force to push or pull that body from rest, or to change the speed or direction of its motion. Newton's second law states that the resultant force of an object is equal to the change in momentum per change in time. This can be written as F is equal to the time derivative of the mass times velocity. Now you're probably thinking to yourself, wait a second, that wasn't what I was taught in high school. We were taught that force is equal to mass times acceleration. So did your high school teacher lie to you? Well, yes and no. Force is equal to mass times acceleration is a special case of Newton's second law. If the mass is constant, it can come outside of the derivative, and the time derivative of velocity is simply acceleration. So yes, force does equal mass times acceleration as long as the mass can be considered constant. This is most of the time valid as an assumption, at least over a small time increment. Newton's third law states that for every action, there is an equal and opposite reaction. There is a balance to forces, and a lot of engineering is about analyzing that balance, as you will see throughout your studies. Only three laws governing motion, eh? Sounds pretty easy. Or is it? Let's try to apply these laws to analyze the takeoff of a commercial jet. Let's start with Newton's second law, force equals mass times acceleration. What are the forces involved in an aircraft at takeoff? During takeoff, there are a number of forces acting on the aircraft. There is the distributed lift force acting on the wings that varies both in the span-wise direction of the wing and in the chord-wise direction as well. There is the thrust of the engines, which also produces a complex distributed load due to the mixing of cold thrust from the fan and hot thrust from the engine core. We then have substantial drag produced by the landing gear and by the entire surface area of the aircraft. Flight control surfaces such as ailerons can also impart forces on the aircraft, and we shouldn't forget to take into account potential loads due to wind gusts. But that is only one side of the equation. We also have to think about the accelerations. In addition to the overall acceleration of the aircraft, there are local accelerations occurring as well. The wings flex, causing different accelerations along the wing, and the flaps and landing gear will begin to retract to reduce drag. As these states of motion continuously change, all of the forces we previously mentioned will also be changing, making the state of motion quite complex to analyze. So the only way to practically do this would be with a tremendous amount of computational and engineering manpower, just to get one answer, the takeoff conditions. Additionally, in design situations where you're trying to develop a new aircraft concept, the constraints around these calculations will constantly be changing, requiring calculations to start from scratch, time and time again. So what can we do about this? Well, as you will learn throughout your engineering career, engineering is about making models, and models are basically simplified representations of what we are really interested in understanding. So for a lot of engineering analyses, we simplify the problem greatly so that we can produce quick calculations that can be used to make early design decisions. For instance, we can take all the complicated physics and aerodynamics of an aircraft and approximate them as simple distributed loads. Alternatively, we can simplify further by reducing the aircraft to a single point mass, with all the complex loads represented as resultant forces. Now you may ask yourself, don't we risk being wrong in our calculations by oversimplifying? Can such simple models really be useful in the context of something so complicated? This is where I need to tell you a big secret about engineers. Engineers are not concerned about being right. In fact, I would argue that engineers are never right. But that's okay, because engineering is not about being right, but being right enough. We will make assumptions and simplifications that make our results ultimately wrong, but right enough to be useful in our design process. But there is a caveat to this. Ultimately, people's lives depend on our engineering designs functioning properly. So it is very important to know the limitations of our engineering models and the consequence of these on our designs. This is why it is so important to focus on conceptual understanding throughout your engineering studies. It is critical for you to understand the concepts behind different analysis techniques and engineering models so that you can properly assess if they are right enough for your application. This is also why you may find your professor paying a lot of attention to whether or not your answer makes sense in the context of the problem at hand. We need to be critical of the results we obtain and not simply follow steps and procedures. But we'll talk more about this in a later video. We have covered that engineering mechanics is the field that describes the motion of bodies when subjected to forces, and that engineers use simplified models to describe this behavior. Then why are there so many different courses on mechanics? Essentially, we start at the simplest case and slowly introduce more and more complexity into our models. At first, we'll start by modeling bodies as rigid objects, examining Newton's laws of motion for when the body is not accelerating, a course we call statics, and then when the body is accelerating, a course we call dynamics. However, as you will learn, it is not always appropriate to model bodies as rigid objects. Sometimes we have to consider how the material within the body behaves. We introduce the deformation behavior of solid materials in the course Solid Mechanics, sometimes also referred to as Mechanics of Materials. Fluids also behave differently than solids, so we examine appropriate methods to model fluid motion in the course Fluid Mechanics. Even this course can be further subdivided to recognize the differences in behavior of fluid flow that is subsonic, transonic, and supersonic in nature. Then there are aspects such as oscillatory motion and material failure that can also further complicate our engineering models, leading to courses in vibrations and fracture mechanics. And this is a highly simplified view of these topics you'll be examining in the context of engineering mechanics. In order to describe the forces involved in our models, we have to examine concepts of energy and energy transfer in the field of thermodynamics. That thrust in an aircraft engine doesn't just appear out of thin air. And in parallel to all of this, we need to equip you with many additional tools to perform your analyses. Different fields of mathematics, programming skills, and even drawing skills become necessary tools in this engineering toolbox. Wow! As you can see, it takes a lot of effort to be wrong like an engineer, but also right enough like an engineer.